Good evening, everyone. I'm Calvin Joseph, and today I'll conduct your week 11 problem solving and doubt clearing session for the NPTEL course, Digital Electronic Circuits. So let me share my screen. So today is the week 11. We'll be considering the following. That is, basically they are known as data converters, which sir has told a lot about in this week lectures. That is DAC, which stands for digital to analog converter, and ADC, which stands for analog to digital converter. So what I'd like you to guys to recall is that you are studying digital electronic circuits. You are studying digital electronic circuits. So what do these circuits need? They need digital information. Right? You need information, digital information, right? So let us say a simple example. You have what is known as you want to measure the temperature. So you have a room, you have a big room you have, right? You want to measure the temperature. Let us say you have a small temperature sensor. So usually what happens is your temperature sensor will generate a voltage sense, like known as the sensed voltage, which is proportional to your temperature. Okay. Now this is a voltage, so it is analog. Okay, it is varying continuously with time. What you would need to do is you'll have to make it digital, right? So you have to pass it to what is known as an ADC. That is your analog to digital converter. Now you will have the data, V data, right? You'll have the data of the sense, temperature, everything. You have the data. This data will be sent to some large microprocessor, microcontroller, DSP, FPGA, something, right? And that will, based on that, it will control the temperature. It may have some, what you say, some thermostat, right? This will control the temperature. So the room temperature, if you have to control it, you need to sense it. You need to sense what is the temperature of the room. Based on that, you convert it into digital using an ADC. That data you send it to your digital processor. It could be a microprocessor, it could be a microcontroller, it could be an FPGA. And then that will generate a control command which goes to your thermostat. Okay, so this is a one small example of where you need an ADC. So your information, your real world information is analog, but you need to convert it into digital domain. Then you also have a DAC. right? Digital to analog converter. That also has various ways. So what we do is we have a signal. Okay, we have a analog signal. It could be a sine wave, it could be a triangular wave, it could be a random wave, any wave that goes to your ADC. This is how we represent the ADC. What does this mean? This is your input signal, right? It's your input signal here. And from here, you have these are the various bits of the ADC. Suppose this is D9. This is your MSB. This is D0. This is your LSB. Okay. So these bits we represent like this. This means there's not only one signal, there are multiple signals, right? Because there are multiple digital signals, right? So that is there. Then you have your microprocessor, microcontroller, some digital platform that will send another set of bits, which actually is translated like this into a number of bits here. And that goes to your DAC here. And then this will be your reconstructed signal. Okay. So this is how you have a DAC and a ADC. So when sir started teaching, he first started with teaching the DAC. DAC. So I have a question. Is DAC faster or ADC faster? And why do you think could be the possible reason?
Yeah, ADC is faster.
ADC is faster. Why?
Um, the approximation the following is the DAC method slower now.
Mm, could you send a message? It's not clear, sort of. Or probably your is my network poor? Or,
I think it's mine.
oh, let me connect to LAN also. Mhm. Okay, you're saying ADC is faster. Okay. Why do you think ADC is faster? Like, what is your reasoning? Okay, so successive approximation, that is one ADC. Okay. So I'd like to tell you that DAC is usually faster than ADC. So DAC are of, like, if you see the successive approximation register ADC which you have, it has an inbuilt ADC. Sorry, inbuilt DAC it has. So when it is doing the conversion from analog to digital converter, it requires a DAC. Okay, it requires a digital to analog converter. So if it is using some subsystem that is a DAC, that has to be much faster. Okay, that is usually much faster. Okay, so the DACs, you can have what is known as the binary weighted resistor DACs, right? You can also have R to R ladder based DAC. And usually you keep uh, an op amp at the DAC's output to prevent loading. Okay, we don't want loading to occur, so we use an op amp at the DAC's output. That can be, inverting amplifier, inverting or non-inverting amplifier. Okay, so this is certain bit of the DAC. Next, you have an ADC, okay, which is your analog to digital converter. So can you recall what are the various ADCs are discussed in this lectures? What were their names and all? Okay. So R2R ladder, SAC, SAR. Okay. R2R ladder is for DAC and successive approximation, yes, that is for ADC. What other things? So, Sir had mentioned something known as the Flash ADC. Okay. After Flash ADC, there is something known as your counter based ADC. Then Sir discussed about the single ramp based ADC. Then there was the dual ramp based ADC. And finally, Sir talked about the SAR, that is the successive approximation register ADC. Okay. So let us start with the questions because the questions are very useful and everything. They will give us more understanding about the concepts as well. So let's start with question 1. Sorry. Question 1. So you have a DAC. So what is it saying? It is a 9-bit DAC. And the step size is 30 millivolt. So you need to find what is the full scale voltage output of the DAC, right? So if you recall, DAC, as I mentioned, it has 9-bit DAC, right? This is a 9-bit DAC. So does D8, D7 go on to D0. Okay. And it will generate some voltage, V analog, right? So if so you have D8 to D0. If all the bits are 0, what will be the V analog? Can you tell me? If all the bits are 0, what will be the V analog output of the DAC?
Is 0.
Correct. It will be 0. Okay. Now, if it is 0, 0, 0, 0, 0, and this D0 is 1, then what will be V analog?
30 millivolt.
Correct. 30 millivolt. Right?
30 millivolt.
Yes, yes. So this is your step size. Okay. So what is the maximum value which the DAC can go to? Right? So you have to go for 2 raised to 9 minus 1. Because this is the integer equivalent of 9 bits, right? So your full scale output will be 2 raised to 9 minus 1 into 30 millivolt. How much is that? Sorry?
15.34.
Yes, so it will be 15.32 volt.
15.36.
15.36 volt. Okay, fine. Okay, similarly, the resolution is similar to 30 millivolt, right? And that corresponds to 1 upon 2 raised to 9 minus 1. Okay. So that's why your answer is B. 30 millivolt and 2 raised to 9 minus 1. 15.33 volt and 1 upon 2 raised to 9 minus 1. Okay, so this is regarding the resolution of the DAC. So this is the correct answer we got. This is slightly confusing. But if this is the correct answer, then this is the correct option. You cannot have 2 raised to 9 minus 1 as the resolution. Resolution is, what does resolution mean? It is like you would have studied in measurements and all when you have done your 12th, everything. The smallest thing which it can detect, which it can measure. Okay. So that's why 2 raised to 9 minus 1 is the maximum. So you go for 1 upon 2 raised to 9 minus 1. Okay. So we'll go to the next question. This is the question. Okay, so now if you will see what circuit is this? What circuit comes to your mind when you look at this circuit? Hmm? Could you repeat once more? So look at the circuit and try to let me know what do you think is the circuit doing? What is the function of such a circuit? It's a circuit given randomly to you. You will soon have your NPTEL exam. You have studied a lot of topics, everything. Look at the circuit. What strikes your mind? So if you look at it, you will see there is R to R. So this is basically your R to R ladder based DAC. Okay. Then you will see this is your MSB bit, second bit, third bit, this is your LSB bit. And this is always connected to ground, right? Now, the order of importance goes from this side, MSB to LSB. So this is our R to R ladder. So what is this? This is basically a 4-bit DAC. Okay. Then we have an op amp. Can you tell me what would be the gain of this op amp?
It is non-inverting.
It will be, could you text it a little bit, it wasn't very clear. Okay, gain is 2, correct? Gain is 2. Because it is non-inverting amplifier, that's why what is the gain? 1 plus 1 upon 1, so it is 2. Now, what is the overall value, right? If you remember the gain of the DAC or the signal over here, that is V analog, that is what? 1 upon 2 raised to 1 plus 0 upon 2 raised to 2 plus 1 upon 2 raised to 3 plus 0 upon 2 raised to 4. So what is the value of V analog then? You can even text me on the chat. V analog is 1.25. So V analog actually is 0.5 plus 0.125. So that is 0.625 volt. And your V output is gain into V analog. What is your gain? 2 into 0.625. So what is that? What is 2 into 0.625? Oh, okay. This is 1.25. Correct. Okay, so it is 1.25 volt, right? So you have a 4-bit DAC and 1.25 volt. Okay, so this is a very simple question. Only thing was when I saw the question, I got confused. I was thinking the voltage should be 0.625 volt. But actually there is a gain of 2, which is due to the non-inverting amplifier. Okay, so there are certain subtle ways to trick you. So be alert, be watchful, and constantly, be on your guard. Okay, so now DAX we have done. Now let us try to understand ADC. There's a question for ADC. A minute. So we'll consider a question regarding ADC. So they're saying it's like a design question. You're all engineers. So you are already designing systems, or you would be designing systems once you start working. So this is a very, very small, simple question. So you are supposed to design an ADC. Okay, designing an ADC takes sometimes years for people to design it. But this is just a question for you, just to test your understanding. Okay. So you have to design an ADC for a speedometer to calculate the speed of a rotating wheel. Okay, of a rotating wheel. Now, the dynamo which converts rotation of wheel into analog electric voltage can generate 0 volt, means it's stationary, the wheel is not rotating, to 15 volt wheel rotating at top speed. Okay, they have not told 0 to 300 RPM, all that they have not told. They have told that there is a something rotating, and based on that, you have a dynamo which measures the speed. Okay, so that the analog signal which is coming is between 0 to 15 volt. So that is the range. Now, what do you want? You want the uh, accuracy. The accuracy, it should be able to detect 0.3 volt, which actually will correspond to a change of 1 LSB. Okay, this is corresponds to a change of 1 LSB. So you want to use a flash ADC, right? You want to use a flash ADC. So you must tell me to go from 0.3 volt to 15 volt range. You want to go from 0 to 15 volt in steps of 0.3 volt. How many number of steps are required? How many number of steps are required? You should first tell me. 50. Okay. You need to detect 50 number of steps. Now, what should be the bit size of the ADC? How many bits are required? For this case, how many bits do you require? 6 bits. So Kiruba is saying 6 bits. So if you need 6 bits, how do you get it? You do log the base 2 of 50. That will come out to be how much? I don't have my calculator. Can you tell me, or let me use MATLAB? Well, okay, if you have calculated, can you tell me log 50 to the base 2? So we want to do log of 50. 5.6439. Yeah, 5.64 you also got. So it is 5.64, correct? So it is 5.64. So you must take the ceiling function of that. So ceiling of log 250 will be, no, this is correct. The ceiling of 5.64, that is actually 6. Okay, so that's why as you are right, you need 6 number of bits. So that means you need a 6-bit ADC. And they want it to be a flash ADC. Flash ADC means it will convert fast, quick. Delay is not there. So if you want a flash ADC, how many number of comparators do you need? So for a 1-bit ADC, you need 1 comparator. For a 2-bit ADC, you would require 3 comparators, if you recall. And there is a question also which you will see. How for a 2-bit ADC, you need 3 comparators. So then, if you need a 6-bit ADC, how many comparators you would need then? What would be the formula? It would be 2 raised to n minus 1. So how much you will get? How many number of comparators do you need in that case? Yeah, you'd require 63. So you need 63 comparators. Correct. So, yeah, so you have solved, very good, you have solved this question 3. So basically, like, it is you are trying to finalize what are the requirements of your ADC. Then further, you have to design a flash ADC, you'll have a huge team to design it and all that. Okay, so that's the process which slightly industry will follow. The starting bit part. Next, we'll go to the next question. So, quantization operation is to be performed on a 0.75 volt sinusoidal signal such that each quantization step is of value 2 millivolt. How many bits should be required to perform such a quantization? So, what do you mean by quantization? Can anyone just tell in simple words what do you understand by quantization? Quantization is making analog as 0 or 1. That is like digitization. So quantization is basically, suppose you have an ADC, right? ADC over here. You have a signal over here. Okay. These are all the bits. Then you have a DAC here. And this is the reconstructed signal. will these two be the same or will they be different? Because both are analog signals. Different. Okay, they're different. What would happen is, suppose this is your sine wave, original signal. When it passes through your ADC and all, it gets converted like this, right? I'm not drawing it properly, something like this. So basically, you have some steps. So this is known as your quantization steps. Okay? And that they have told is 2 millivolt. That is 2 millivolt. Okay? And they're telling us to find out what would be the error. So suppose this is your quantization. Your signal could be here, could be here, it could be here. In which case the error is more. Let me draw better. You have, this is one part of a signal, this is another part of a signal, this is another part of a signal, where actual value was, in one case, it was this much at this time. In the next case, it was in the middle. And in the next case, it was much closer to the top. Which one has more error? Which of these options has more error? Can you tell me, the blue one, the green one, or the orange one? Third one. Okay. What about Kiruba? Which one do you think has more error? The first one, second one, or third one? Third one. Okay, I think because my drawing is wrong, that's why it is uh, not. You guys have told the wrong answer. So actually, the let me draw again better. You go to the new page. So this is the signal. For all cases, this is the signal. This is a reconstructed digital signal. Same. They all have the same quantization. Okay. In between this point to this point. Okay. Same. In between this point to this point in time. In time. One, your actual signal value was somewhere here. For the second case, your actual signal value was somewhere here. In the third case, your actual signal value is somewhere here. Which one has the most error? First has more error. Okay. What about Kiruba? What do you think has more error? Okay. So what, if you will notice, so you let us see uh this is 2 millivolt. This is 2 millivolt. This also is 2 millivolt, right? Now, this error will be around like 0.5 millivolt. This error will be like some minus 0.5 millivolt. But this error is 1 millivolt. So when it is at the center, that time the error is maximum. Right? When it is in between, that time the error is maximum. So the maximum error that is possible is 1 millivolt because your quantization is 2 millivolt. Okay. Okay, so this meeting will end in a few seconds. Then I will restart the meeting on the same link. So you don't need to worry. You just have to join in the same link. Okay, so because we don't have the premium version of Zoom, we are limited to 40 minutes. So this meeting will just end in within 10-20 seconds. Then I will restart the meeting with the same link. So you just have to join in the same link. Okay, don't worry. And we'll proceed from this part onwards. Okay, so let's continue. So the maximum error which we got is 1 millivolt and the quantization is 2 millivolt. Now, in your question, if you remember, you have to perform it on a sine wave of 0.75 volt. So what is this 0.75 volt? That actually is this. So you have a sine wave, right? So this is your 0.75 volt. So the actual range of the signal will be how much? It would be 1.5 volt, right? And you have to quantize into within 2 millivolt. So what would be the number of steps you'd require? Hmm? How many number of steps changes in LSBs in bits you'd require? What is the range? The number of steps actually will be equal to 1.5 volt, that is your range, divided by a resolution quantization, that is 2 millivolt. Hmm. That will be 750. Yes, correct. Right? That is 750, right? So if your number of steps is 750, how many number of bits do you need? Will again be, this ceiling function of log of 750 to the base 2. Hmm. Okay, so let me just repeat since Kiruba is joined again. So maximum error will be 1 millivolt because your error is maximum when it's in between, in the middle. Okay, and your quantization is 2 millivolt. Now, you have to find what is the number of bits required. So since they told the signal is a 0.75 volt sine wave, actually it is 0.75 into 2. So in overall peak to peak you have to do. So it is 1.5 volt. So that means your range is 1.5 volt here. And your quantization is 2 millivolts. So the number of steps you require is 750. And the number of bits you will get by this formula. So can you calculate and tell me what will be the value of this? Or you tell me what is the value of log of 750 to the base 2? What is that value? That will be 9.551. Okay. And the ceiling of that is 10. So you require a 10-bit ADC. Correct. Correct. Both of you are correct. 9.55. So you require a 10-bit ADC. Where a 10-bit ADC and DAC would be needed for this example. So let's go to the next question. So successive approximation ADC constitutes a DAC as a subcircuit, yes or no? True or false? Okay, so Suresh is saying true. So it is true. Successive approximation ADC uses a DAC internally. So DAC will generate some value. So how many? Let me ask another question. How many comparators does a successive approximation ADC require? Does it require 10? Does it require the number of bits? Or how many comparators do you think it will need? It requires one, correct? It requires one. So basically, what it will have. This is your input sampled and hold signal, and this will be the signal sent from your DAC. Based on that, it will generate 1 or 0. Based on what it generates, it will have some logic. It will have a digital logic. It will have some registers. It will have some clocking. It will have some latches, flip flops, etc. So that is the overall logic. Okay, you also have learned various things. You have learned finite settling, FSM, or that from one state to another state, how do you go, the evolution, everything. So all this you could use and you can generate a digital logic. But to generate the analog value, you need a DAC. Okay, you need a DAC. That is inside your successive approximation ADC. Hmm. Okay, let's go to your next question. So what does it say? The clock frequency of a 10-bit ADC, question 6. This is a 10-bit counter-based ADC. How do you find the conversion time? 10-bit counter-based ADC. And so what do you have? You have your F clock is 2 megahertz, right? So what is the conversion time for this ADC? So you have a counter-based ADC. Here also you have here also you will have some plus minus. This is the sample and hold signal value. And here you have a counter. Okay, you have a counter which is going up, going up, going up, going up. This is your counter. When your counter goes above the sample and hold value, right, then you generate a pulse. So initially, suppose this is your counter. Okay. This is your counter like this. And here, your signal which you have sampled and held is like this. Another time it goes like this. So this is your sample and hold signal. Okay. What it will do is it will start counting the time from 0 from this time. When this goes again, it will count like this. So this is your time duration. Okay, time of how much time it takes for conversion. Similarly, here like this, it will rise. Over here, it will fall. So this is again your time for conversion. Okay. Now, what you have to do is you have to measure this time. When it is at over here, what are all the bits? All the bits are 0, 0, 0, 0, 0, 0, 0, 0. Then and there will be something known as a F clock. Okay, there's a F clock, very high frequency clock. I think we can also do certain simulations as well. So this is your F clock, which is at a rate of 2 megahertz. So then it will be 0, then it will become 1, then it will go higher, higher, higher. Like that it will go. So it happens at the rate of 2 megahertz. So now your value, your number has gone to 00111 00100. It has gone to 00111 00100. So can you find it in decimal? How much will this value be? How much does this value correspond to? Two 28. Okay. So it corresponds to 228. Then your conversion time will be what? 228 into 1 upon 2 megahertz. So what is that value? Simple. 228 divided by 2 into 10 to the power minus 6, right? So that is 114 into 10 to the power minus 6 seconds. So it is 114 microseconds. Okay, correct. Okay, so this is how we have solved this sum. So let's go to the next question. Yeah, correct. Thank you. So we have to consider 5-bit successive approximation ADC converter. The reference voltage of this is VREF is 32 volt. So we have to find what is the value of analog input voltage at the digital output of the ADC is this much. Okay. So you have a successive approximation converter, and then it is 5 bits, right? Your VREF is 32 volt. 5 bits means how much it is? 1 bit, 2 bit, 3 bit, 4 bit, 5 bit. If all are 0, 0, 0, or if all are 1, 1, 1, 1 also can happen. This all 1, 1, 1 corresponds to what in decimal? This means 0 in decimal. All 1, 1, 1, 1, 1 corresponds to how much in decimal? I mean to say, it was 10000. In decimal, how much it corresponds to? 31, correct? So this corresponds to 31. Correct. And this will correspond to 16. So now your range is between 0 to 32. But your decimal part can be up to 31. And what you're actually going for is 11110. So that would correspond to how much? That would correspond to 30, right? So that's why your answer is 30 volt. Your VREF is 32 volt and your decimal equivalent can go up to 31. So if you have one bit is less, it will go to 30. Okay. Okay, so we'll go to the next part. Next question. We have a single RAM type ADC. Where we have R is 1 kilo ohm, C is 1 nanofarad, and VI is 1 millivolt. After how many clock cycles the ADC will generate a digital output if Vx is 128 millivolt? Okay. So R and C. What's the time constant? 1 kilo ohm, 1 into 10 to the power 3 into 1 nanofarad is 1 into 10 to the power minus 9. That is 10 to the power minus 6 seconds, right? Now you have, so this is also known as your slope. Okay. Now you have like an integrator based arrangement, right? Integrator based arrangement where your V instantaneous of your integrator is 1 upon RC into VI into T. Okay, into T. So now, what is your VI? Your VI is 2 millivolt. 2 millivolt. RC is what? 10 to the power minus 6. And your T is what you need to find out. Your V instantaneous is 128 millivolt. VI is 2 into 10 to the power minus 3. And this 10 to the power minus 6 into T. Right? So, the time required is what? This and this get cancelled. So time required is 128 by 2 into 10 to the power minus 6. So that is 64 into 10 to the power minus 6 seconds. Right? So this is the time required. Then they're saying the clock frequency is 1 megahertz. F clock is 1 megahertz. So this time required is the number of counts into 1 upon your F clock. So you have to find the number of counts that is equal to T into your F clock. So that is 64 into 10 to the power minus 6 into 10 to the power 6. So that is equal to 64. Okay. Any doubts? You want me to repeat it? Okay. So basically what you have in this RAM type ADC is you have something which is going like this until it touches this value, that is your Vx. Okay. And this slope is governed by Vi by Rc. Okay. Slope is Vi by Rc. So this starts at time 0 and this time which it reaches, that is your T conversion time. Okay. When this is happening and when what will happen, there will also be some clocks. Okay, high frequency clock, which is at 1 megahertz rate. And what those clocks will be doing is they will be incrementing a counter. You have studied a counter, right? Counter will start from 0 and it keeps on counting. It counts the number of times that clock has come. You have studied synchronous counter, asynchronous counter, all those things. So when the first clock comes, it will go from 0 to 1. Next clock comes, it will go to 2. Next clock comes, it goes to 3. How long does it go on until it touches this Vx, right? So if it has touched Vx, it will take some time. So that conversion time, T conversion, is what we are calculating. How much time it took? So the T conversion we found out to be equal to 64 microseconds. Now it is counting to it is conversion time is 64 microseconds, but and the clock frequency is 1 megahertz. So how many times that clock has come? One clock, second clock, third clock, fourth clock. In this conversion time, how many times those clocks have come? So that is given by n counts is equal to T into F clock. So that's why it comes out to be 64. Okay. All right. So these are certain things which takes time to realize, but it will make sense soon. So an input sine wave is converted to a 6-bit digital signal. So what is the SNR in that case? SNR is what? 6.02 n plus 1.68 or something. So 6.02 into 6 plus 1.68. How much is this? Okay, 37.8. So that corresponds to this answer. Hmm. If I'm not wrong, actually it should be 1.76. Okay, let us check. Notes are available. Notes, where are the notes? Hmm. Just search, you can find SNR. Hmm. Yeah, 6.02 n plus 1.76. Okay, so let's go to the. So this question, there is some error is there in the answer, but it's a good question. So let's check it. Right, right. So you have to find the value of x. If Vref is 2.56 volt, so what is the value of x? So this voltage is 2.56 volt. This volt is 0 volt, this volt is plus 5 volt DC. So that means this volt is 2.56x, right? So your 2.56 is actually what? It is equal to your 500 minus x plus your 1 upon 4.7 plus 1. And this overall resistance is 500. So plus 500. Okay. So what do you get? You get 501 minus x is equal to 2.56 into 505.7. Right? So what is this value? What will be the value of x? Can you calculate and tell me? Seven 93.59. Okay, what about Kiruba? It cannot be more than 500 actually. So x is basically what? 501 minus 2.56 into 505.7. So what is this value? It's going to be negative. Oh, I forgot something. will be multiplied by 5, right? It's a resistor divider multiplied by the input voltage, right? So it will be 2.56 into 5.7 divided by 5. This is divided by 5. Okay, then can you tell me? Okay, it is 242. Nice solved. Yeah, and I got 242. Correct. Your X is 242. So your X is 242 kilo. Hmm. So that was not among the options. So that's why this was incorrect. Like this question did maybe an error in the answer which they have provided. Hmm. So your resolution also which you can get, it is 2 into your VREF upon 2 raised to what? 8, na? 8 bit. So that is 2 into your VREF is 2.56. 2 raised to 8 actually would be 256. Hmm. No, 2 raised to 8. So your resolution is your span divided by the 2 raised to 8. Because 8 bit ADC. So span is what? 2 into your VREF, that is 2 into 2.56. 2 into 2.56, okay? Upon 2 raised to 8. 2 into 2.56 is 5.12. Upon 2 raised to 8. That is 5.12 upon is 0.02, yes. So that comes out to be 0.02. That actually is 20 millivolt. Okay. That is your resolution. So let's go to the next question. Which of the following statements are true? So which statement is true? Which statement is false? Can you tell me? One is true. Okay. What about two? See, gain error occurs when all the output bits are 0 and the applied voltage is less than full scale voltage. 2 is true. No, 2 is false. Gain error. If all the output bits are 0, it corresponds to offset error. It is dealing with offset error. So that's why 2 is false. Now, for an ADC, the deviation of the values on the actual transfer function from the straight line transfer function is called what? Is it called integral nonlinearity? So what it means, your ADC is converting like this, and this is the value. It should go on like this, but it will curve off somewhat. So that is known as your integral nonlinearity, where you're checking it from bottom. From the bottom, you're checking. Okay, that is called, you're summing it up. How much is the deviation from the bottom to the top? You always start from the bottom to the this instant, how much is the integral nonlinearity? Here, how much is the integral nonlinearity? So on and so forth. Right? So that is why this is called the integral nonlinearity. So this is true. Now for DAC, differential linearity. Error stands for the difference between an actual step width and the ideal width of one LSP. This is false. So this actually is differential non-linearity. If it was written differential non-linearity, then it should have been true. But since it is written linearity, it's not linear. It could be positive, it could be negative, there could be some offset. Everything is there, right? So that's why it is a non-linearity. So 1 and 3 are true, 2 and 4 are false. Okay. Okay. Let's go to the final question. Question 12. So this is a 2-bit flash ADC, right? As I told you, have how many comparators? You have 3 comparators in the 2-bit flash ADC, right? This voltage is 5 volt. Analog input voltage is 3 volt. So I want you to tell me what is the voltage over here, over here, over here. Can you tell me what is the numerical value of that voltage? If you analog, your reference voltage V is 5 volt. This is 5 volt. Right? So what will be the voltage at 1 by 4 V? How much it will be? 1.25. Here, how much it will be? 2 by 4 V, how much it will be? 2.5. Right? And here it will be 3.75. Okay, the meeting will soon end, but we will proceed. In the same link, you'll have to rejoin. So now what will be the values of C1, C2, C3? Will it be high or low? What will be C1? Will it be high or will it be low? So your input voltage is how much? It is 3 volt. So here it is 3 volt. Here again it is 3 volt. Here again it is 3 volt. So what will be C1? Okay, C1 is high. What will be C2? C2 is also high. And what will be C3? C3 is low, right? Now, what is this B1? What is B1? Is it 1 or 0? B1 is 1 because you do 1 and 1, you get 1. Then this is 1. What is the XOR of low and high? XNOR of low and high? So this is 0 and this is 1. What is the XNOR of that? Okay, so yeah, you should preferably be okay. XNOR of 0 and 1 is 0, correct? XNOR of 0, 1 is 0. So 0 and 1 is how much? 0 and 1 is? So 0 and 1 should be 0, right? Yeah. So your B1 and your B0 is 1 and 0. Okay. This is how we have checked about the Flash ADC. This is the question regarding the Flash ADC. Okay, so till here, do you guys have any query? Any issue, any doubts? Okay, summarize the Flash ADC part for the entire session. Oh, theoretically, what is a Flash ADC? Okay, okay, fine. So this is your Flash ADC, right? So your VREF is 5 volt. Hmm. So that means your analog input voltage can range between 0 to 5 volt. Hmm. So it has three comparators. It is flash because it is fast. Your comparator is fast. Like if you have a SAR ADC or you have a counter-based ADC, you increment, you check, you increment, you check, you increment, you check, everything. Here, we are checking at multiple levels. So one I'm checking with 1.25, one I'm checking with 2.5, one I'm checking with 3.75. So the reference voltage, that which is actually a range which you can apply, that voltage is checked simultaneously. So when you check it simultaneously, you get some HHL. Okay. So let us, you get HHL. But this is a 2-bit ADC, right? It's a 2-bit ADC. So it requires only 2 bits. So this 0, they have to be decoded. They have to be decoded. Okay. So that's the decoding part. This does the decoding part. Okay. And this does the comparator part. Hmm. So basically, you can have C3, C2, C1, and you have analog input, right? And you have your digital bits, that is B1 and B0. Let us say. So now, if it's between 0 to 1.2 volt, your input is there. Then all these bits are 0, 0, 0. All these comparator outputs are 0, 0 because everything is less than 1.25. And your B1, B0 also will be 0 and 0. But if it ranges between 1.25 to 2.5 volt, like it is less than 2.5 volt, etc., all that, then what your C1 alone will be high. All these are 0, 0. Then your B1 should be 0 and B0 should be 1. Then if it is between 2 point, sorry, if it is between, there is a 2.51 to 3.74 volt, right? Something slight value. Then what will happen? C3 is 0, but C2 and C1 both will be high. So that in that case, this should be 1 and 0, right? And when it is greater than 3.75 volt, then all are high. Then this should give 1 and 1. So to convert the comparator outputs to these digital bits, you need a decoder, which is this one. This is your decoder. Hmm? And these are your large number of comparators. And a simultaneous comparison. So that's why it's known as a Flash ADC. Okay. I hope this cleared it. Or if you have any more questions, you can further ask. Okay. So this is the regarding the Flash ADC in the session, what we did a lot, we discussed what are data converters, converts ADC analog to digital, digital to analog, etc. DACs are the ADCs are there. A real world example also we checked how if you want to control the temperature for room, you need a sensor, and the sensor is in analog. It will generate a voltage, so that you have to use an ADC. That data goes to some microprocessor, microcontroller, FPGA, something like that, and then that will generate some command which will go to your thermostat. That might require a DAC. Hmm? Then we saw what is a DAC, what is a ADC, then what are different types of ADCs, also what are different types of DACs, and then we solved various questions. Okay, very interesting questions. The questions have been framed very well. These questions are like they're using what and all you have learned, and they are making you think. It is like it is setting you the direction in which you have to think, so that you can work in a real life. What ADC, DAC you may need for your projects as well, and in your workplace and all when you go in the industry, what you require. Okay, so there are various things are there, which the questions are very well set, so that you can try to realize that. Okay, so what I'd like to do now is I'd like to proceed with certain simulations, because simulations are what. So suppose you have decided you'll go with the SAR ADC, Flash ADC, everything. You make a circuit, but how do you know your circuit will work? Then you have to simulate the circuit. So let's just think of certain simulations which we can look into. Let us say, so I've been using Simetrix. Mhm. Okay. ATC DAC 10. Let us see, this is already ready-made example. Okay, let me save the schematic as, let me save it somewhere. Mhm. Here, let me start simulation. This is where I want to save it. ADC, DAC. Yeah, okay, fine. So look at this. When you look at this, what do you see? You have a ADC block. You have a sine wave input voltage. Then all the bits of your ADC are going one by one, one by one, one by one to a DAC, and that is generating an output. Okay. Let us say this is your input. Okay. Let me run it once. You'll understand. Okay, let me now undock it. Are you able to see this? There's a green line and there's a red curve. Okay, green line and a red curve. So the green one is your input signal. The red one is your digitized, quantized signal. Okay, that's what we were discussing regarding the error from quantization. So this is there. I think this is a little bit difficult for you guys to understand. Let us make a simplified one of this. See, ADC, DAC. Let's do 4 bits. Less bits. Okay, it will be easier for you guys. So number of bits, let us say 4. This is it. This also 4 bits. These all are not needed. Indeed. Run it. Yeah. Okay. Now let me unlock it. So the green is your input signal. Your red is the quantized output to the DAC. And these are this D3, D2, D1, D0. These are your bits. Okay, these are your bits. D0 is your LSB. So your LSB will show you the most number of changes, the fluctuations, everything, right? Your D1, your D2, your D3. D3 is your MSB. So that has the least change. Why it has the least change? Because only if this is above 0, it will be high. If it is below 0, it will be low. This is for your MSB. D2 will have slightly lesser changes and D1 will have little more than D2 and D0 will have the most number of changes because it's your LSB, right? You have written in many binary tables, you know that the last significant bit that either changes 0, 1, 0, 1, 0, 1, it changes a lot. Okay, what I'd like to point out is, if you notice over here, there's stepwise change. But over here, there's no change. Why? Because if you recall, the slope of a sine wave is minimum close to its peak, right? And so the change in the input voltage is not so much. So this change of this much, this change from here to here, it is less than how much a LSB would detect. That's why there is no change. Okay, that's why it remains fixed. In these other places, it keeps on changing because the value is changing. The value is changing. So this is how, and this is what we call, in our lab, we use this test a lot. This is known as a loop back test. Okay. What does it mean? We have an input signal, which is a sine wave. It is a test signal that passes through my ADC, then that passes through a DAC, and I get an output again displayed. So what is the advantage of doing all this is, you know that your ADC is working, you know that your DAC is working and all. Okay, so just, you would need to test everything a lot. Okay. And in your project, you need to use an ADC, you may need to use a DAC. So I'd always recommend, if you have an ADC, you should also try to have a DAC. It enables you to debug, to check whether your ADC is converting correctly or not. Okay. So cause you can see D3, you can see D2, you can see D1, you can see D0. But if you want to see all these signals actually in a practical test setup, you would require 3-4 channels you would need. which is difficult. But if you want to see the DAC signal, you just require a one channel. So that enables you to quickly and fast know whether your ADC is working fine or not. Okay, that is one thing. Okay, any queries regarding this? So this is slightly, it may be a bit new to you guys, or you guys may know it very well as well. But is this something which sir has not shown in the class, right? So this is regarding ADC and DAC. Okay. So over here, we have used ready-made blocks. Okay, you have ready-made blocks are there for digital to analog converter. Ready-made blocks of an analog to digital converter are there. Okay. There I see there is some ADC block. What does it do here? Okay, this is regarding a clock. This is not okay. This is DAC. What is this? Okay, a counter. Okay, this is a counter. DAC output. Okay, fine. Enable reset, enable B, reset B. Okay, this is a bit not necessary. Okay, okay, all right. Don't say. Let's try making a new Simetrix schematic. Let us save it as Flash ADC. Okay. So let us use this circuit. So we have a reference 5 volt. Let us place a connector. Connector. This is VREF. The same VREF I can access here. I place a resistor. Let us say resistor 1K, another resistor 1K, resistor 1K, resistor 1K. Connect the ground here. So this I connect here. This I connect here. 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 Okay. Now I need a comparator to place digital log behavior comparator. Mm, conductors, comparator. Mm, comparators. Okay, comparator with ground. So, wait, just say, please, where's that thing? Compare. So, a comparator will give plus or minus. Okay, let us say plus, let us say VREF. This, let us put ground. Okay, and this, like this here. Okay, we have to also add a input signal. So this is like an input signal we can have like this. Same input signal here. This is your input signal. This is my input signal Vn, right? So over here, I will compare it between what and what. Plus is going to my input signal and minus is coming here. Okay, good. So there's a minus here and here is my input signal. Just connect. This is my input signal. Okay. So this will be repeated like this here. This is connected here. This connected to input. Similarly, it's repeated here. Minus is connected here. This is connected to input, right? This is C3, C2, C1. So place, this is C3. So I'll rename it now C3 C1. Okay. Let us just check at this stage whether it is working or not. Okay. This is my V input. Just see whether there's any error. Okay, what it didn't run. Okay, no analysis has been specified. Choose analysis transient. Okay, run. Did it work? Why it didn't run? Okay. This is where it is. What is C1, C2, C3? Okay. These are digital. So let me make it a digital thing. Digital, digital. Okay. So super. Let me run it once more. Yeah. There is some kind of non-ideal behavior. Don't know why. Advanced options. Yeah. Let's run it now. It's better. No. I think the comparator has an issue. Comparator seems to have an issue. Hmm. Comparator should give a digital output, but it's giving analog output. What is the reason? I have to ground. So we place comparator with ground. I, I have to see. I'm not very sure what is the difference exactly. But they shouldn't theoretically make much of a difference. Let's see. No, these comparators are not working correctly. Okay. It's going negative. Comparator output should not go negative. Hmm. Comparator gives So our comparator block is creating an issue. Does anyone have any suggestion? Anything else we could try? Comparator is not working. Hmm. There's a creating issue. Help also is not there. Let me see help. Not exactly clear. So something better. Let me check this once. Let us check now. Okay. It seems to be much better. So this is shows the comparators. What is the distance is? Let me make it very small, 1 milli. Output high voltage 5, output low voltage 0. Okay. So let me make it 1 milli. 1 milli. Run it now. C1 is changing, why C2 and C3 is not changing? Okay. Okay, let us make this 0 to 5 volts. Let us run now. Yeah. So C1, C2, C3 also are changing accordingly. But it should have an offset. Okay. Or sine wave. Offset is 2.5. Peak is 5. Let us see. Okay. No. Peak also should be 2.5. No. Yeah. Okay, so C3, C2, C1 all are working. Very good. Now let's complete the circuit. So you have a XNOR gate. Okay, XNOR gate followed by a AND gate. Okay, let us see B1. Let us first make it. So B1, how it makes it by C1 and C2. Okay, A is digital and okay, AND gate is not there. Okay, AND gate is there. Right. This is your B1. Place the probe here. Now you want to find B0. B0 you need to place XNOR gate. So place digital XNOR gate is there. How? You can choose a XOR and then followed by a NOT. So you have XOR gate you have. Okay. We'll follow that by a NOT gate. Where's NOT gate? Inverter is good. You have inverter. over here. Okay, so you have C2, C3, XOR, and then NOT, so XNOR happens. Then you have an AND gate. Okay, you have another AND gate. This over here. Comes from here, and the other input of the AND gate comes from C1. Okay, C1. Or we can directly take C1. These are module ports, so they are connectors. They're connected. And this will generate B0. That is over here. B0. Let us place a probe also over here. Fine. Okay, so let us run it once. Right? We undocked it. Okay. So what you will notice over here is, first let us go to the sine wave. Okay, let us understand the sine wave. Sine wave is starting from 2.5. It is going to 5. Then again going to 0 and so on. Okay. So let us say at 0. When it is at 0, what will happen? C1, C2, C3 all will be 0, right? Because it is less than 0. Now it will go slightly above 1.25. When it goes slightly above 1.25, what will happen? C1 will turn on. If C1 turns on, all C2, C3 all are 0. C2, C3 don't turn on. So if it has gone to 1.25, above 1.25, then what should happen? Your B1 should be 0 and your B0 should be 1. That is this case, right? So B0 is 1 and B1 is 0, right? Let us consider case when this case. If you look over here, B1 is 1 and B0 is 0. So in that case, let me place a cursor. I think cursor will better. Over here one cursor, over here one cursor. Okay. So in between these two cursors, what do you see? You see C1 is high and C2 is high, right? And if you will see the red voltage, you would notice it is between 2.5 to 3.75, slightly. Cursors are slightly off track. Let me just bring it within the range. So you'll notice it is between higher than 2.5 and less than 3.75. In that case, what happens? Your C2 is high and C1 is high, but your C3 is low. And then what happens? Your B1 is 1 and your B0 is also 1. B0 is 0, so B0 is 0, right? Now, let us check the case when all are 1. That is between here to here. If it's between here to here, what do you notice? Your C2 is 1, C3 is 1, C1 also is 1. Then what happens? What is your input voltage between the range? It is actually greater than 3. It is greater than 3. Greater than 3.75. Here if you will go, your input is 5 volt, something, right? Almost 5 volt. So between 3.75 to 5 volt, B1 will be 1, B0 will be 1. Similarly, the other ranges are there. Any doubts? If you want me, I can even explain it again. If you no issues, I can summarize it. Like any specific queries you have? For this, I don't know. Like, I think you can refer to Sir has one book which he has suggested in his references. No, let us see what book he has suggested. You can check this book, which Sir also is a author. You could check this book. If you can access this book, you can study that. Right? So specifically, I have not referred to any book for these things. These are like more by practice, more by checking simulations, seeing what my seniors have done, and all I've come up, learned all these things. you can also you can refer to this book. You can also try simulating. And like, I really feel that simulations are very useful, to grill the concept into a person, right? So how step by step the blocks have been made. What is this difference of 1K, 1K? What you could do, you can change it from 1K, you can make it 100 ohm or 10K. See what is the difference. See, we faced an issue because, see, this comparator, why is it working? Because this is a ideal comparator. It's a very good comparator. It's an ideal block. But the comparator which we actually put in the start, that is a practical block. Okay. So there are certain reasons. So probably what has happened is I've not put the comparator as in a circuit in the way it should be. Something I messed up, something I've not put properly. That is why that was not working. Hmm. So those things I further, if I get time, I can change it and do. Okay. So this is how certain logic circuits you can also build and you can also check it. So this software, Simetrix Simplest Elements. Let me go to the main, this one. Okay. This is a free software. Simetrix Simplest Elements version is a free software. The other one is a paid version. It is expensive. And what I observed is the Simetrix version, you can have a larger number of logic gates, digital gates, etc. You can test it. In the simplest one, there is certain limitations in the number of logic gates, which I had to learn in the hard scenario, the hard way. So you can preferably you can use symmetric elements for you to learn all these things. Okay, there are various things like which I'd like to further tell. Like you can go to examples. There are certain examples are there. So what I did was I just went to the example, opened the file, and then modified the file. So the various blocks are already pre-configured. You can already check it, right? So then you know what you should do for ADC, what you should do for a DAC. All these things are there. Hmm. Generic digital, what to do for a gate, what to do for a counter, what to do for a register, what to do for a shift register. Hmm. Pseudo random generator to demonstrate generic shift register. This also sir had shown, but I had not simulated it and shown to the students. But you can also refer to all these things to get this concept very well understood. Okay. So thank you for joining. I hope this was a useful session for you, and I enjoyed it. Hmm. Thank you. Okay, okay. Okay, but what is about gate exam? Yeah, gate exam you can give. Yeah, you should give. Uh, so gate exam, I'll tell you the mistake I made was I did not study analog and digital. Like that was what, because I'm from electrical background, I didn't need to, like analog digital, the weightage was less. So I skipped those topics. But now I'm getting an opportunity to learn them again. So gate exam is like any competitive exam. For preparing, you should, go through the syllabus very well, be very thorough with what and all you know, strive for the higher weightage topics, and solve previous year questions. Yeah, that the way to go forward. Okay. Uh, Job market for electronics is going up and down. Job market for any field is going up and down currently. So we cannot comment. So, but electronics is quite good. Okay, so the meeting will end in 1 minute. If you want, I can restart the meeting and we can further continue. Okay. Okay. Yes. Yes. Okay. We'll see you next week. Okay. Thank you.